Alright, so this is a short video of the implementation of dual contouring on a uniform grid that we did. So let's start. Here we have a visualization of the volume that we're gonna, whose surface we're gonna extract. This is a torus, and so we have a grid here that is represented by these transparent circles. And then the volume that is represented by these red circles. So the grid, so the volume basically lives inside of the grid, right? And where the volume is red, those are values of the sign distance function, which is sampled, that are negative, and where the points are black, that's where the sign distance function is 0, and when where they're transparent, that's essentially positive sign distance function values, so outside of the volume. And so we have this grid that samples the sign distance function, which creates a torus. And we take that and we extract the points on the surface, right? So these are the points on the surface. If I turn off the volume, you can see they live only on the surface. And we use those to connect them into a mesh. So here's the mesh. And we connect all of the surface points into triangles, essentially. There are a few different ways to connect them. So, for example, we can use a blocky scheme that gives us like this Minecraft-like look, which is a worse approximation of what the surface actually is, but it's nice and stylistic. We have the centroid scheme, which is a smooth approximation, so that's the barycenter of the surface crossing the individual cubes in the grid. So I'm not going to talk about the actual dual contouring algorithm much, but yeah, so this is just the barycenter of the edge crossings of the cube. And then there's the QEF, which looks pretty similar to it, but it's supposed to represent sharp features better, because it also uses the normal data at the edge crossings to better infer if there's a sharp feature inside of the cube. So that would be easily seen if I change the torus into a kind of a cube shape here, like a box. If I align it with the grid, so you can see it's fairly sharp right now, like this edge, for example. Especially so if I make the resolution kind of correct. But if I was to change it to centroid, you see it fails to capture the sharp feature. It's much smoother, right? These are the surface points. Again, I can change it to QF, and now it straightens out the edge much better. That's basically the bulk of the QEF stuff, and the dual contouring stuff, and that was done all on the GPU using compute shaders. The final mesh is pulled out from the GPU and rendered using Unity's built-in mesh filter renderer thing, which is, you see, this is essentially the cube that gets pulled out. There are a few different shaders that I wrote to debug and show stuff off. So this is a flat shader, which is why if I change this to a torus, you can kind of see the flat shading across the triangle. Now there are other shaders. We can also do like a wireframe view, so this is difficult to see. I can change it to, let's say, unlit, so now it's much easier to see. In addition, what else do we have? We have like there's normal shading, so these are the normals of the surface that are kind of approximated using the sign distance function. What else? We also have different shapes here, so pyramid. Octahedron, and here's just three-dimensional noise, which looks pretty cool. Something like this. Let me show the flat shading again. And we have matrix transformations. So you can go in here and rotate the shape. Which is pretty cool. Here's the volume of the noise. What else? You can increase, decrease the resolution. So this is less triangles, more triangles. Increase the size of the grid. That's pretty much it. I don't think there's much more to say. Thanks for watching.